Okay, thank you for invitation. Can everybody see my document camera that's showing the papers and pens?
Yes, I can see it except Yan, I guess.
Oh, sorry.
Jan, what happens when you click Spotlight Video?
When I click Spotlight Video. Okay.
Yeah, today I will talk about the coherent constructible correspondence for toric projective bundles. So my plan is the following. First, I will talk about the original version of the coherent constructible correspondence, which is in short CCC. And I will give a rough statement of my main theorem. But to make a precise statement of my theorem, it requires knowledge from sheaf of categories and their global section. So after that, I will revisit my main theorem. And if time permits, I will talk about the conjecture for general toric fiber bundles. So what is a CCC? A CCC is a version of homological mirror symmetry for toric varieties or toric stack. The first idea was introduced by Bundle. An equivariant version of it was proved by Fang, Liu, Truman, Jaslow, and non-equivariant version in full generality is proved by the Kuwagaki. So it states the following. Let X be an n-dimensional toric variety, then it states that there's an equivalence between the DG-derived category of X and the other category, which I will write sheaves on Tn under lambda sigma. This is a DG category of constructible sheaves on Tn with singular support lies in lambda sigma. So Tn is an n-dimensional real torus. Lambda sigma is some subset of cotangent bundle of T star Tn that I will explain in a moment. So recall that constructible sheaf is if we are given a space and space has a stratification, and sheaf on that space is called constructible if its restriction to each strata is locally constant sheaves. Also, notion of singular support. This is the following. So let M be a manifold and F be a sheaf on M. So we define singular support of F that will be a subset of T star M defined by a closure of set of covectors, which I will write in X to C in coordinate, such that if there is a function f that is fx is 0 and df is c, so I think we better see a picture. So here is x, here is a c. We choose a small ball around x, and we choose f such that fx is 0, the fx is c. And there will be a x will lies on the f inverse of 0. We can consider two subset that f inverse of minus infinity to epsilon, f inverse of minus infinity to minus epsilon. So there will restriction to b. We will have two values of sheaves f, which is on intersection of intersection of this part and intersection of this part. So definition of singular support is that is value of sheaf f inside the f inverse of minus infinity to epsilon is not isomorphic to its value of f on f inverse to minus infinity to minus epsilon. So the idea is that the singular support measures, detects the covectors that stalk of sheaf does not propagate. So I will use following notation. If lambda is a subset of T star M, and I will write sheaves lambda M, this is a category of constructible sheaves on M, such that its singular support lies in lambda. So let me give you an example. Let base space be an R, and its cotangent bundle will be isomorphic to R2. And suppose stratification of M is given by its origin and complement. Then first, consider space looks like this. Here I draw real line, which is M, and I will assume that lambda is equal to M, which is R. Then category of constructible sheaves on M with singular support lies in lambda will be isomorphic to local systems on R, because there is no codirection that fails to stalk of sheaves are being not isomorphism, which means that stalk of sheaves is isomorphic to at each point, and this means that this category is object of this category is actually a local system on R. And since R is contractible, this is just a category of bounded complex, so vector spaces, which I will write in perf K. And suppose in this time, we have M here, and if lambda looks like this, we have one M, base space M, and we have one co-fiber at origin. Then, if constructible sheaves satisfy the whose singular support lies in M, lambda, then its value on each strata will be determined by its stalk at each point on this each stratification. So I will write each stalk as a, say, stalk at origin as A, stalk at negative numbers as B, stalk at positive numbers as C. And we can see that this positive codirection lies in singular support. This means that if we restrict from here, which contains A, to this set, which contains B, there will be a map from restriction map from A to B. And by the same reasoning, there will be a map from A to C. So sheaves on constructible, a category of constructible sheaves on R with singular support looks like this. This category is isomorphic to equivalent to representation of this type of fiber. Let me give you a slightly different example.
So may I ask, so you consider everything derived or non-derived because you somehow change it. A line in one, you say that something is equivalent to the category of perfect complexes, and here you say, is it what, abelian category, exact category, derived category?
Yeah, all categories are derived.
All right. So you simply omit this dB for all categories which will appear.
I'm sorry?
You omit this dB derived because representations of the quiver for people who work on quivers, it's just a Abelian category. When you write that something is a representation of a quiver.
Ah, right. Ah, okay.
Yeah,
Maybe
so
I should write
it
DB.
can be a
like
convention, but then.
Yeah. Yes. Thanks. And let's consider next example. Here, lambda looks like this 1/2 co-fiber at origin and base space. Again, its value of stock of sheaves on each strata, I will write as A, B, C. By the same reasoning as in the second example, we will have a map from A to B. However, in this case, this negative part covector does not lie on the singular support, which means that map from A to C should be isomorphism. So in this case, this category is isomorphic to the category representation of A to quiver. Let me give you a higher, one-dimensional higher example. So in this case, I will assume M is R2 and consider lambda singular support looks like this cone of dx, which is cone of dx so on y-axis, which will looks like topologically base space R2 and half R2 glued along the y-axis. So I will use the following kind of convention. So locally, again, this the stock of sheaves will be determined by stock at each point, which are contractible. So I will draw a small ball around here, which will be this circle. And I draw this base of singular support as a line. And the convention is that I will draw these covectors as hairs on this line so that its sheaves of categories, sheaves of constructible sheaves, category of constructible sheaves will be isomorphic to representation of A to quiver, which go against the hair. So let's go back to the statement, our CCC. Here, X was a toric variety, and I will write sigma as a fan of X. Lambda sigma is a conical Lagrangian subset of cotangent bundle of torus, which is determined by the fan data of X. Lambda sigma is roughly defined as union of, for each cone in fan, we consider orthogonal complement of sigma, and we take a product, and we product by minus of sigma. Let me explain what this means in examples. So suppose X is a C star, then fan of X will be a point that lies on one-dimensional space. Here we have origin, and since this one-dimensional lambda sigma will lies on T star of S1, which I will draw in a cylinder. So, and I will identify S1 with the R mod Z, then the vectors that is orthogonal to 0 should be all the points on S1. And vectors that minus to zero vector is just the zero vector itself. So lambda sigma corresponding to sigma C star will be just base space S1. But if X is a C, the fan of C will be a union of point at origin and one vector, one dimensional cone along the one direction. In this case, we have two cones. One is point origin, one is this half line. By same reasoning as in the first example, the subset of T star S1 corresponding to point is this base space. And we have one dimensional cone here. The point that is orthogonal to all the vectors lies in this half line will be just a zero, which I will draw here. And we take product with the minus of these vectors. So I draw half line that corresponds to this one-dimensional cone. If X is a CP1, then fan of CP1 is given by one-dimensional cone, two one-dimensional cones and one origin. And you can see that by same reasoning, the zero will correspond to base S1. This one vector will correspond to a half line at the half cofiber at origin, and this other will correspond to negative of cofiber at origin. Let me give you a one-dimensional higher example. At X is CP2, then we have a fan looks like this, which lies in R2. And lambda sigma will be a subset of T star of T2. And I will draw T2 as this square identified with each parallel edges. And in this case, we will have seven cones. One is origin, one is one-dimensional, three one-dimensional cones like this, and three two-dimensional cones like this. Again, this origin would correspond to base space of torus. However, in this case, let's consider this upper oriented half line. Then the vectors that are orthogonal to this half line from the definition will be just horizontal line x-axis on the R2, horizontal line on the square. And we take the product with minus of this direction. So we, using the convention I draw here, this will look like this figure. By same reasoning, the vectors that are orthogonal to this direction is this edge. We take minus of this direction. And the singular support subset corresponds to this will be this edge with hairs looks like this. Similar reasoning shows that this arrow, third arrow, corresponds to this subset. And for two-dimensional cones, the point that is orthogonal to all the vectors in this two-dimensional subset is just the origin, only origin. So, and if we take minus direction of it, then if this is sigma, then minus of it will be looks like this. So if we have a bigger picture, the subset correspond to this two-dimensional cone will be set of cofibers at this origin. And by same reasoning, the set of subset of singular support that corresponds to this will be looks like this and this. No. Will be this, and the covectors correspond to this dimension will be this subset. So it is just all the covectors at origin. So we usually draw this figure as like this. This picture will appear later again. So let me give you a rough statement of the main theorem. So I will use the following, for a while I'll use the following notation. The M be a manifold. Lambda is a subset, a conical Lagrangian subset of T star M. Then the theory of microlocal shifts of Kaishira-Shapira can be restated in fancy way, says that there's a Kaishira-Shapira shift mu sh lambda. This will be a shift of categories on lambda, such that constructible shifts, category of constructible shifts on M with singular supertalizing lambda will be a global section of this shift of categories mu sh lambda. So CCC can be restated as a equivalence between dBx and this global section. And their recent work, Andrew Harder and Harder-Katzarkov stated that there should be a version of CCC for toric fiber bundles, but they did not give a precise statement of this claim, but they provided example for toric P1 bundles. So this following, that Y be a variety. This will be a base of toric fiber bundle, and consider a line bundle on Y. And we will think about projectivization of direct sum of O and L. And this will be a P1 bundle over the Y. Then claim is the following. The derived category of coherent sheaves and total space of this project P1 bundle over Y is isomorph equivalent to global section of some constructible shift of categories, which I will write FL. That is, this will be a shift of categories on lambda sigma P1. This lambda sigma P1 was the subset which appeared in the CCC for fiber P1. Recall that here it is. Our picture. For CP1, lambda sigma looks like this subset. The claim is that there is some constructive shift of categories on this set whose global section is equivalent to derived category of total space. So my main theorem is can be said half of the previous statement for Pn bundles. So let Y be again base variety, and we choose n line bundles, L1 to Ln on Y, and we consider projectivization of all direct sum of O L1 Ln. And this will be a Pn bundle on Y. Then claim is that dB, derived category of total space of these Pn bundles, embed into some global section of lambda sigma Pn, which appears in the CCC original CCC for Pn. And there is a sheaf of constructible sheaf of categories on lambda sigma Pn, that this will be a sheaf of categories on this set. You can see that our original version of CCC state looks like this, which is can be stated as a global section equivalence between derived category and global section of some constructible sheaf of categories and skeleton, some Lagrangian subset. And P1 bundles, we have similar statement, and equivalent statement for Pn bundle is this. But in a moment, I will describe what is meaning of this sheaf of categories and what is meaning of global section of that. And remark is that if Y is a point, then this total space will be just a projective space Pn, and this recovers ordinary CCC for Pn. Yes, of course, we expect that this will be equivalence. Surjectivity is not yet proved. And also, one remark is that if we define toric fiber bundle as a fiber bundle with toric variety fibers, say X, and we define toric fiber bundle as a fiber bundle with fiber X, toric variety X, with structure group is given by complex torus, which lies naturally X on X by definition of toric variety. And if we define toric fiber bundle as this, then toric Cn bundle will be that is Cn bundle is just vector bundle, and being a toric means that its structure group can be reduced to C star n, which is n copies of C star. So any toric Cn bundle is direct sum of n line bundles. We have same reasoning. Toric Pn bundle will be fiber is projective space and structure group is PGL n plus 1, but structure group can be reduced to C star n inside of this group. You can see that if transition map Gij is given, then this Gij vectors through map to C star n plus 1 inside GL n plus 1. So if this is given by lambda 1 to lambda n, this embeds PGL n plus 1 as 1 comma lambda 1 comma lambda n. And this is just the image of 1 comma lambda 1 comma lambda n in this torus. What this means is that any toric Pn bundle is a projectivization of toric C n plus 1 bundle, which we know that direct sum of n plus 1 line bundles in this case. Yes, so any toric Pn bundle looks like projectivization of OL1 direct sum of OL1 to Ln. And we see that this is full statement for any toric Pn bundles. Okay, so in our theorem, we saw that the statement involves notion of sheaf of categories and their global section. And I will give a precise meaning of that categories and these notions. In their work, Harder-Katzarkov give their own definition of perverse sheaf of categories on a surface. And in fact, this definition is a little generalization of notion of perverse sheavers due to Kapranov and Schuttman. And this notion of perverse sheaver is just a categorification of keyword description of perverse sheaves on the disk. So let me explain this in detail. There's a theorem known to many people that claims the category of perverse sheaves on D, disk D, and we choose n marked point inside D, and suppose stratification is given by these endpoints and complement, then this category is equivalent to the category of following data. It consists of, its object looks like these tuples, vi, w, phi I to ci. I is varies from n1 to n, where vi and w's are vector spaces, and phi I and to ci are linear maps from vi to w and w to vi. And we impose conditions such that identity minus composition of phi and psi are invertible. So rough idea is that if we are given a purple sheaves F, then this Vi is a vanishing cycle at each Pi's, and W will be a nearby cycle on the complement of Pn, and phi i's and Ci's are the map appears from theory of purple sheaves. That is, one is generalization map, one is the canonical map. So the idea of proof of this theorem goes like this. We have Pn marked points inside the disk, and we fix one base point on the circle. We fix one endpoint on the complement of P1 to Pn. We connect these 2 points, and we choose some arcs that connects. Let me write this. Yes. Connect this P1, its marked point, to this point we chose. So connect like this, which I will write at K1. Connect like this, which I write K2. And we may connect this to Pn to this point by Kn. And if we write this union of these cuts into K, the proof of the assignment of Vi and W's for F, which is dependent on choice of K, is defined by, given by the stock of the shift of compactly supported cohomology of F. We only take the first cohomology of that and take a stock at each Pi. And for W, we choose a stock at this B. The point is that if we choose some branch cut looks like this, then perverse shifts on this this with this marked points gives a constructible sheaves on this subset K. So the idea of Kapranov-Penn-Schuttman is the following. This will be such categorification of previous idea. We define K coordinate-based perverse solver, say on the disk. Here K is the choice of branch cut that appeared in this picture. It's a collection of data that consists of Ci, D, Phi I, where Ci and D are DG triangulated categories, and Phi I are functors from Ci to D, such that there should be the condition that correspond to invertibility of this identity minus Phi Ci. This condition corresponds to notion that called spherical functors. So a precise definition of spherical functor is not needed in our talk. The point is that roughly this gives a constructible shift of categories on K. That is, the Ci's will be stock at P1, each marked point. And we have K, and stock at edges, any edges will be D here. We have a map from Pi to D, which is phi, which will be right phi 1, phi n. And the difficult part of this assignment is that define the stock at this n-valent point. Yes. So what is this stock at this point? I will not give a full description, but for trivalent point, it's like this. Stock at this point is given by A to D, which is a representation of category D on quiver A to quiver. So stock at this point, trivalent point, is given by, say, A to D. And the object of this category looks like some object in A in B, arrow B in D. And it comes with the natural three maps, one that assigns this representation to A, one assignment that assigns a B of this quiver, and one that assigns the cone of this map. So let me write this as a F. Yes, so this is how the constructive sheaves on constructive sheaf of categories in K looks like.
Probably this is how you define them.
Yeah, how we define. And this can be thought of as a sheaf of categories on disk. And we define global section of this Schrober as a homotopy limit of the diagram that coming from the constructive sheaves on K. So let me explain meaning of this in example. So recall that our singular support that corresponded to P1 looks like one cofiber and S1 lies in T star S1. I will define by deforming this half line to this way. This space will be looks like S1 and 2 half cofibers. And I will define Herbert Schober on this space. This is actually not a K. This will be K. Actually, this K is not a subset of disk, but disk minus 1 point. But definition is almost agree with the disk case. And I will define the sheaf of categories whose generic stock at edge D is perf K. And then for simplicity, I will assume there's no marked point. So there will be no CIs in this example. So from this, I say that at trivalent point, we assign A2 representation of A2 quiver with coefficient in perf K. We assign A2 perf K at this point. So recall that yes, and our generic stock is perf K, so each stock at edges are perf K. And the restriction maps will be given as following. Let me draw a bigger picture. Here we have perf K, A2 perf K. Object will look like to A to B, F. We have perf K here. We have perf K here. we define a functor that sends a tail of A of this quiver representation, say A, and sends B to here. And similarly, we can define tail and head of A to perf K here. So let's try to compute global section of this shovel. And this K can be decomposed into two copies of this trivalent graph, which can be drawn as a union of two copies of this picture. And if you remember that so yes, its value at this point is given by A to perf K. So this can be thought of as a to quiver representation from here to here, whose singular support lies in this fiber, which can be written as A2 representation of perf K. So we may write this let me draw this as a, say, AB. This can be also thought of as a CD. And the diagram that coming from this constructible sheaves of K means the following. We have two copies of A2 perf K, and we have restriction map to perf K cross perf K, which sends head and tail to this product category. We have one more copy of A to perf K, which sends again head and tail to this category. So claim is that the global section is homotopy limit of this diagram. So what this diagram, the meaning of diagram is the following. We identify each head, each tail of two arrows. We identify two heads of these two quivers, which will give two copies of arrows. This will be identified. So we have quiver looks like this. And we know that the representation of this quiver is actually the Bayes-Lensin's description of DBP1. So we can see that this gives a kind of CCC for P1. So global section is actually P1 and is isomorphic to DBP1. So, and the perverse sheaf of categories defined by Harder-Katzarkov is just a slight modification of this perverse Schober. So for example, we have, they include the monodromy around, for example, some cycle in K, for example, S1 in this picture, by deforming restriction functors. So for example, we had the following perverse Schober that assigns A to C to A, let me change C Okay, so let's fix this generic stock by C. A to C at each point, we had a functor that assigns head and tail to each stock at edge. For example, they give a following modification. We have same K here. We have same A to C here. We have same stock C here. We have same restriction map T, T, H, H. But in this case, we modify the one of the restriction maps by composition with phi. Here phi will be a sum autoequivalence of generic stock category C. So this can be thought of as a this can be thought of as the sheaf of categories whose fiber C, and if go around by C, this local system on S1 is given by autoequivalence that is given by phi. And we can define global section of this type of sheaf of categories in a similar way in that the perverse Schobers. You will have similar diagram coming from this type of fever. And what Harder-Katzarkov proved is that the derived category of total space of P1 bundle, projectivization of O and L, is equivalent to global section of sheaf of categories on this lambda P1, a sheaf of categories F on lambda P1, lambda sigma P1, and F is a perverse sheaf of categories given by this picture, where phi is given by tensoring with L. So phi and generic stock is given by derived category of coherent sheaves on base space. We know that phi tensoring with the line bundle gives autoequivalence of derived category of space. The claim is that this global section of this category is derived category of total space. And so let's go back to the main theorem again. So the idea of sheaf of categories on the surface was that include monodromy around each cycle by deforming restriction functors by autoequivalence of generic stock, for example, tensor by L in this example. And my statement was that this derived category of total space of this PN bundle embeds into global section of sheaf of categories. I will write in FL1 to LN on a skeleton that corresponded to PN. So what is this sheaf of categories? So this will be some constructive sheaf of categories, lambda sigma Pn, and generic stock at point, generic stock at generic point is given by derived category of Y. Well, but we may use a complicated theory of general sheaf of categories and define this FL1 to LN in a concrete way, rigorous way, and compute global section. But in this case, this global section category admits more easier descriptions. So recall that on the surface, the monodromy around S1 that correspond was tensor by L in this example, in this theorem. And we may expect that the monodromy for this shift of categories on a lambda sigma Pn will be given by tensor by L1, tensor by L2, and tensor by Ln. So let me explain this in an example. So for example, let n be a 2. We saw that for P2, the singular support corresponding to P2 looks like this picture. We have torus, 3 edges, and some hairs on that, and any co-fibers at origin. As we deformed, recall that for P1, lambda sigma P1 was actually this subset, but we deformed this into this type of picture. We do similar thing. We deform this subset into, we slight move these 2 side edges to this way. So it will be looks like, after deforming, this. So f of L1, L2, which will be a shift, some constructive shift of categories on this set, will be looks like this. Recall that, so if we choose some small region around this edge, it will be locally looks like this. And we saw that the category of constructible sheaves with this singular support looks like a figure like here. So our description of FL1, L2 is the following. We have stalk at each region divided out by edges. Stalk at each region will be C, category C. I will write C as a derived category of base space. And we will have the restriction functor from that corresponded to each singular local singular support that corresponds to these edges and these edges. And we also have this map, this map, this map, this map, this map, this map, this map. But look at this area and this area. They are actually the same area on the torus, but my claim is that these 2 parts is related by monodromy of C, which is tensor by L1. So if we go around from here to here, we expect that stalk at this point is differ by tensor by L1. If we go from here to here, stalk at this point to at this point and this point will be differ by L2. So this region and this region will be also differ by tensor by L1. So for example, this region and this bigger region will be differ by tensor by L2. So I can make the following claim. The global section of this shift of categories F, L1, L2 on this singular support subset is actually following category. That is category of fiber representation of dBy, which was a generic stalk, with the relation and condition of the following form. Let me draw again. So representation of dBy that looks like this. Here's torus, and we have the fiber like this, And suppose let me write stock at this point as A, and our claim was that stock at this point and this point are differed by monodromy of L1. Stock at this point and this point was differed by A tensor L2. And let me write this stock at this region as a B, and then this stock at this point will be differed by tensor by L2. Stock at this point will be differed by L1 with this stock, so it will be B tensor L1 inverse L2. And let me describe the last component as a C, where A, B, C are object of dBy. So our claim is that if we have a nice theory of constructible sheaves of categories on higher dimensions, the global section category on this singular support subset should be a category of Quiver representation of dBy with some condition and relations that looks like this. A and this point, these points are identified with these points by tensor by L1. These points and these points are identified with tensor by L2, L1, and tensor by L2.
So this is a definition, yeah, of the global category, because you do not have independent definition of this sheaf. Do you understand correctly? Because you are in higher dimensions, so Kapranov and Shechtman cannot help you. Yeah, so when you speak about constructible sheaf of categories, maybe you want it to be perverse, and then I don't know. You should have it to be defined independently on the quiver description, and your claim should be indeed a claim, theorem. But I do not understand whether you have this definition independently on the claim.
Well, I'm not sure I understood your question. So, yes, I think there's two ways to think about this. So, we take a definition of global section category as this category, or we develop a general theory of sheaf of categories of in higher dimension generality and prove that general description for global section is actually isomorphic equivalent to this category. So I think
I think the second way will be too difficult, because in general you do not have such a description even for perverse sheaves. In higher dimensions, it's kind of Kapranov and Shechtman were lucky in the case that they have such a description in the case of a disk. Even if you take the Riemannian surface, it's much more complicated than the disk because there is no quiver. If you go to higher dimensions, it seems to be way more difficult. So as a definition, this is fine. It's nice, but as a claim, I don't know. But anyway, go ahead because you don't have
Yes, then
much time.
for safety, I will define the global section as this category. Is that okay?
Yeah, that's okay.
And our main theorem can be restated as the derived category of total space embeds into the category we described before. So claim is that we have category of cubic representation of dvy with some relations and conditions that appears from singular support of lambda sigma pn. So claim is that this was for P2, and my claim is that such description also appears for Pn for any n. Yeah, I think I will stop here.
Okay, thank you. Thank you very much. And the questions? Okay, there is something in the chat.
Yes, I have two questions. Hopefully they can.
Yeah, you can read them, and everybody can read them.
Yeah, so the first question is that do you also expect surjectivity? Yes. And our higher homologies of Schober you described expected to represent anything meaningful. I think your second question is about.
I have a question to the second question because I do not understand what are the higher cohomology. As far as I know, there is no definition of the cohomology.
I think her question is coming from this description of.
Yeah, I understand, but in the higher dimension, there is no.
So for
okay, go ahead. Excuse me. Yeah.
So for in this example, Schober on a disk. In fact, this H1K is how can I say, supported on degree 1. That means all other degrees or all other degree for I is not 1. This HIKF is 0. So there is no information coming from higher homologies.
So that's rather a question about perverse sheaves. Yeah, if you consider perverse sheaves with respect to the stratification you mentioned, then whether it's true that it's every perverse sheaf is pure, which means that it has cohomology only in 1 degree, which seems to be unlikely, but I'm not sure. It's a sort of a Lagrangian picture.
You mean?
Yes, it's a question about perverse sheaves, because as for Schobers, it's complicated. You have some stratification, which you described at the beginning of your talk, and you consider sheaf, which is perverse, probably with middle perversity with respect to this stratification. And so the question is whether the cohomology sits in the single degree.
So your question is, are you asking about this, say, for higher dimensional example, or example that on a disk or surface?
Probably the question is for higher dimensions.
I'm not sure. So, I don't know if this equivalence should be that is similar to that of this study. For first homology.
Would be strange. I don't know. Maybe for some miraculous reason. By the way, what prevents you from replacing Pn by something more complicated?
Yes.
I have a related question that I placed in the chat as well.
Yes. I can't see any chat.
Yeah, I don't see any. Okay.
I think I sent it only to the Galaxy person.
Probably Galaxy will answer. So this Galaxy.
Sorry.
Okay.
I'll cut and paste to everyone.
Yeah, but now you can just unmute yourself and say.
Yes. Okay. What I wrote was, you referred to lambda sigma as a skeleton. Do you expect then a similar theorem for vibrations by varieties mirror to exact symplectic manifolds?
Yes. And Jan's question was that what happens for general toric fiber, and yes, I have a conjecture for general toric fiber. The proof of this description for PM goes like this. This category actually admits semi-orthogonal decomposition that coming due to Orlov. And this is actually coming from the fact that derived category of PN admits exceptional collections that allows to describe derived category of total space. But for general toric variety, unless we assume projectivity, we cannot make 100% that there will be exceptional collections or some easy description for this derived category of total space of toric fiber bundles. But I conjecture the following. This is not yet a rigorous statement, but we have the quotient description of toric variety. So let's say X be some toric variety, and we have some kind of description that coming from quotient. For example, CPN, we have Cn plus 1 minus origin modulo C star. And we expect, I expect that the family version of this construction will appear for general toric fiber bundles. So I expect that general toric fiber bundle will look like some direct sum of line bundles on a base, let me write X, Z, Y, modulo some subset corresponding to Z sigma modulo G. And I also expect that from the keyword description, it can be thought of as a two-step modification, one from fiber, one from the description of this description of this the conical Lagrangian coming from fiber, and the monodromy data coming from general structure of fiber bundles. So I expect that similar pattern will appear here. So for example, if X is some arbitrary variety, and we can assign lambda sigma that corresponds to X, and we can draw similar diagrams like this. This will give some kind of fibers on a torus, and I expect that monodromy data is coming from the description of this G. So for example, in this CPN, G is actually can be described as a home. Let me write here. Kernel of home from sigma one-dimensional cones to home of lattice to C star. So if we have number n for CPN, home from sigma 1 to C star will be C star n plus 1, and home to n C star will be C star n. The map is given by lambda 0 to lambda n to lambda 0 inverse lambda 1 lambda 0 inverse lambda n. If you let the lambda 0 to be 1, this is just 1 lambda n to lambda 1 to lambda n. And we can see that the monodromy data for Pn is corresponding to these monomials appearing in the description of the G. So I expect that for general toric fiber bundle, this fiber-wise quotient, this group G will provide the monodromy data for this type of description required to describe Glover section. Does that answer your question?
Somehow, yes. By the way, what is your restrictions on Y, on the base? Is it projective or what?
Projective, of course. Fine. Okay. Well, I don't see any restriction.
Okay. Yeah, of course, kind of, I don't know, just speculative thing that you can try to go beyond the bundles. Yeah, fiber bundle. You can allow some more complicated sheaf over Y. I don't know whether Ludmil did it for P1. Well, anyway, more questions? Pengju has question. Hi. Okay, you can just ask.
Maybe I can explain a little bit, in more detail. Yeah, so to prove this toric fiber CCC, I was wondering, can one use like the matching? So on the left hand side, you have objects like you pull back sheaves from the base and tensoring with some line bundle and twist by some line bundle on the fiber. if you do not do any twist, if you I just give you an object on the base and pull back on the toric bundle, does that go to some structure? Does that go to some? Sorry, let the train pass first.
Okay.
Does that go to something supported on the fiber over 0 with some coefficient? If that does, then can you do something like do some twisting so that you can flatten that fiber over 0 on the right-hand side to some arbitrary line bundle? You know, without a base, if you just have a point,
yes,
then just the structure sheaf on the toric side goes to the fiber over 0 on the torus, and line bundle goes to some other twisted polytope sheaves. So I was wondering if that philosophy or strategy can work in your case here. That might be helpful to prove subjectivity.
Yes. Yes. That is true. That's true in some sense. So I think, for example, in this proof of this theorem, we identify each SOD component inside this category. The motivation for finding such component is that you can see that, for example, in ordinary CCC, so for example, O corresponded to the sheaves that supported on this contractible contractible area, and O1 will be corresponded to in the triangle like this. And the motivation for finding these components is coming from that. For example, if we want to find the component that corresponds to O1, we kind of take quotient of this triangle, but in this case, coming from equipped with some monodromy. So if we take if we kind of take a quotient of this equivariant description to torus non-equivariant description, it will look like union of this part inside this part inside this part inside this.
Yeah, that's right.
So, and we can, in fact, prove that the corresponding SOD component is that representation of this type. So we have, if the rule is the following: if we identify this to this, we take kind of identifying translation that corresponds to taking monodromy around 1S1. So if we write stock at this point as B, this will be a stock. This stock at this point will look like B tensor with L2. Stock at this point will be tensor L1 inverse L2.
Yeah, I understand. So I guess maybe my question or suggestion is that if you can consider the image of line bundle, fiber-wise line bundle, but base you can pull back anything. These guys on the right-hand side show that they generate like they in the sense that if the harm from these guys to any stock is a zero, then or I don't know to something is zero, then that guy has to be zero in the sense of a compact generator.
Yeah. You're talking about PN only.
What's that?
You are talking about PN case.
No.
Or any projective toric.
Any projective.
Any projective?
This will be
And it's
generated
smooth
by
projective.
Yes.
You can use line
The
bundle.
smooth projective variety admits the exceptional collection coming from line bundles. And I think his idea is that
not necessarily.
not necessary. Oh, okay.
Not you don't have to be exceptional collection. I just say they generate. That's what
Yes.
Okay.
And the second question is, can one use the Kawasaki style proof, namely matching? I expect.
Kawasaki like says, okay, so you have this P1 skeleton, like a circle with two lines. You don't dissect that as you do on the base. Maybe he dissect as a circle, and a circle plus a line, and a circle plus a bottom.
Yes, I think to prove this type of theorem in full generality, I cannot imagine.
Maybe in that case, one has to use this wrapped constructible sheaf with coefficients and do some matching on a fine patch first, and then you can just do some machinery of gluing to finish up the job.
Yes. I'm trying that.
I'm not sure to great detail.
Yes, I'm trying, but have not result yet.
Okay, yeah, that's all.
More questions?
Yeah, I have a question about just Harder-Katzarkov surfaces. So for the main theorem, when you say toric fiber bundles, do Harder-Katzarkov surfaces work as? Okay, and then so there I'm setting n as 1, and even though the fan looks similar, it can look similar. One can use the fan similar to the fan for P2, but if I'm setting n as 1, I really want to look at the singular support for P1 there.
You have closure surface for 1, and you want to describe this as a fiber bundle over P1 with fiber P1.
So I'm asking, in the main theorem, it sounds like we're setting y as P1. My question is, are we setting n as 1, and should I consider the singular locus for P1 or for P2?
Should be P1.
Okay, thank you.
More questions? Well, if not, let's thank the speaker. Thank you very much for very interesting talk.